Welcome back to Whispering Universes, where tonight we venture to the furthest reaches of our solar system, to a realm of darkness and cold so profound that even the sun appears as little more than a brilliant star among countless others. We're going to explore one of the most intriguing mysteries in modern astronomy, a puzzle that has occupied some of the world's finest minds for the past decade, a question that reaches back to the very formation of our cosmic neighborhood 4.5 billion years ago. Somewhere out there, far beyond the orbit of Neptune, beyond the realm of Pluto and the scattered disk of icy worlds we've only recently begun to catalogue, something massive may be hiding. Not a comet, not an asteroid, not another Pluto-sized dwarf planet, but a genuine planet, perhaps 5 times more massive than Earth, tracing an enormous ellipse through the outer dark on an orbit so vast that a single year on this world would span 15,000 Earth years or more. We cannot see this planet directly. No telescope has yet captured its faint light against the background stars. No spacecraft has visited it. No human eye has witnessed its distant form. And yet, over the past decade, a collection of brilliant scientists examining the strange behavior of distant objects have become increasingly convinced that something substantial must be out there. Something whose gravity is gently shepherding the orbits of smaller worlds in ways that cannot be explained by chance alone. This is the story of Planet 9, the ghost in the outer dark, a world that may represent the most significant discovery in planetary science since the detection of Neptune in 1846. It's a search conducted not with dramatic announcements or sensational headlines, but with patient observation, careful mathematics, and the kind of methodical detective work that characterizes the best of modern astronomy. Every few months, new evidence emerges. A distant object is discovered whose orbit aligns with predictions. A computer simulation refines the possible locations. A survey telescope methodically sweeps another section of sky. The search for Planet 9 reminds us that even in our own solar system, even in this neighborhood of space we've studied for centuries, profound mysteries remain. It humbles us with the recognition that something as large as a planet could hide in plain sight for all of human history, too distant and too faint for our instruments to detect until now. It challenges our assumptions about how planetary systems form and evolve, forcing us to reconsider whether the architecture we see today represents the configuration that emerged from the solar nebula, or merely the current snapshot of a long and dynamic history of planetary migration and gravitational interaction. Tonight, we'll explore the evidence that suggests Planet 9 exists, tracing the chain of reasoning from the strange orbits of distant objects to the mathematical models that predict where this hidden world might be. We'll consider what Planet 9 might be like as a physical object, imagining its possible composition, its temperature, its geological character, whether it might harbour moons or rings in that distant darkness. We'll examine how astronomers are searching for this elusive world, the technical challenges they face, and why, despite years of patient effort, the planet remains frustratingly just beyond our grasp. We'll also contemplate what Planet 9 means beyond the specific question of whether it exists. This search represents something larger, a reminder that discovery in science often comes not through sudden revelation, but through gradual accumulation of evidence, through the slow refinement of hypotheses, through the willingness to pursue a question even when the answer remains uncertain. Whether Planet 9 exists or not, the search itself teaches us about planetary dynamics, about the outer solar system, about the formation history of the planets we know so well. As you settle in tonight, perhaps already feeling the gentle pull of sleep, let yourself drift outward from Earth, past the Moon with its ancient cratered face, past Mars with its rust-red deserts, through the asteroid belt with its tumbling rocks, past massive Jupiter and ringed Saturn, beyond distant Uranus and Neptune, out into the realm of scattered ice and rock, where sunlight grows so faint that noon resembles a moonlit night on Earth. Out there, in the darkness, a world may be waiting. Tonight, we search for it together. To understand why astronomers believe Planet 9 might exist, we need to begin not with the planet itself, but with the strange behaviour of much smaller objects that orbit in the outer solar system, in a region we call the Kuiper Belt and beyond. These are worlds of ice and rock, remnants from the formation of the solar system, too small and too distant to have gathered into larger planets, preserved in a deep freeze for billions of years. The Kuiper Belt begins just beyond Neptune's orbit, about 30 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, roughly 150 million kilometers. The belt extends outward perhaps to 50 astronomical units, though its outer boundary remains poorly defined. Within this region, astronomers have discovered thousands of objects, ranging from tiny fragments to worlds like Pluto, Haumea, and Makemake, each following their own elliptical path around the Sun. Most Kuiper Belt objects behave as we'd expect. Their orbits tilt at various angles relative to the plane of the major planets. They travel on ellipses of different shapes and sizes. Their orientations in space appear random, distributed without particular pattern. This randomness makes sense. These objects formed from the primordial disk of material that surrounded the young Sun, and over billions of years, gravitational interactions with Neptune and with each other should have scrambled their orbital orientations into a fairly uniform distribution. But beyond the classical Kuiper Belt, out past 50 astronomical units, we find a population of objects that behave very differently. These are called detached objects or scattered disk objects, worlds whose closest approach to the Sun keeps them well beyond Neptune's gravitational influence. These objects shouldn't interact much with Neptune or the other major planets. Their orbits should reflect the random conditions present when they formed, with perihelions and aphelions pointing in all possible directions. Instead, when we examine the most distant of these objects, those whose orbits carry them more than 150 astronomical units from the Sun at their farthest point, we find something remarkable. Their orbits cluster together. Not perfectly, not in a way that's immediately obvious, but statistically, undeniably, these distant worlds tend to reach their closest approach to the Sun in roughly the same direction. The points where their orbits dip nearest to the inner solar system align within about 30 degrees of each other, clustering in a way that probability suggests should be extraordinarily unlikely if their orientations were truly random. Imagine throwing a handful of darts at a circular dartboard from across a room. You'd expect them to land scattered across the entire board, hitting all regions with roughly equal frequency. But if instead every dart landed within a narrow slice, say between 12 o'clock and 1 o'clock, you'd immediately suspect something was influencing their trajectories. A magnetic force perhaps, or a wind, or some feature of the room creating systematic bias. This is what we see with the most distant detached objects. Their perihelia, the points of closest approach to the Sun, cluster in a way that seems to defy random chance. Additionally, the planes of their orbits tilt relative to the main planetary plane in correlated ways. These correlations become more pronounced when we consider only the most distant objects, those least likely to be influenced by Neptune or the other known planets. The first hints of this clustering appeared in 2003 with the discovery of Sedna, an object whose 11,400-year orbit carries it from 76 astronomical units at closest approach to 937 astronomical units at its most distant. Sedna's orbit seems strange, too detached to be explained by Neptune, too circular to have been recently disturbed by a passing star. As more detached objects were discovered through the 2000s and 2010s, the pattern became clearer. These worlds were telling us something. Their orbits were being organized by some force, shaped by some massive gravitational presence that we had not yet identified. By 2014, astronomers Chad Trujillo and Scott Shepard published a paper noting the clustering of orbital arguments of perihelion for distant detached objects. They suggested that a massive planet in the outer solar system could explain the pattern. This observation planted the seed that would grow into the full Planet 9 hypothesis. The statistical odds that this clustering occurred by chance were becoming too small to ignore, falling well below the thresholds that scientists use to declare a finding significant. The Kuiper belt and the detached objects beyond it were whispering a secret. Their orbits were not random. They were influenced. Somewhere in the darkness beyond, something massive enough to gently tug on these distant worlds was leaving its fingerprints in the architecture of the outer solar system. In January 2016, Konstantin Batygin and Michael Brown of the California Institute of Technology published a paper in the Astronomical Journal that brought the Planet 9 hypothesis into sharp focus. Their work represented not just an observation of strange orbits, but a comprehensive mathematical and computational analysis demonstrating that a previously unknown planet could explain multiple puzzling features of the outer solar system simultaneously. Batygin and Brown began with the clustering that Trujillo and Shepard had noted, but they went much further. They ran extensive computer simulations, modeling the evolution of the outer solar system over millions of years under different conditions. They tested scenarios with various numbers of distant objects, different distributions of mass, different potential perturbing forces. They asked a precise question: what could cause the observed orbital clustering to arise and remain stable over the age of the solar system? The simulations revealed something striking. If you place a planet of about 10 Earth masses in an eccentric orbit with a semi-major axis around 700 astronomical units, tilted relative to the main planetary plane, the gravitational influence of this planet naturally organizes smaller objects into precisely the kind of clustering we observe. The planet doesn't need to pass close to these objects. Its gravitational field, weak but persistent over millions of years, subtly shapes the orbital evolution of distant worlds, shepherding them into aligned configurations through a mechanism called mean motion resonance and other dynamical processes. The mathematics underlying this conclusion draw on principles of celestial mechanics developed over centuries. When two objects orbit the Sun, they exert gravitational forces on each other that vary as their relative positions change. Over long timescales, these varying forces average out, but they leave lasting effects on the orbital elements, the mathematical parameters that define each orbit's size, shape and orientation in space. For distant objects on highly elliptical orbits, the dominant gravitational influence comes from the most massive planets, primarily Jupiter and Neptune. But if another massive planet exists far beyond Neptune, its influence, though weaker due to distance, operates on objects that Neptune barely affects. The key is time. Given millions or billions of years, even weak gravitational forces can produce dramatic changes in orbital configurations, especially for objects in the outer solar system, where orbital periods stretch into thousands of years and where few close encounters occur to disrupt the slow gravitational sculpting. Batygin and Brown's analysis identified specific orbital signatures that Planet 9 should produce. The planet's gravity would tend to cluster the perihelion arguments of distant objects, aligning where these objects make their closest approach to the Sun. It would also tilt the orbital planes of some objects nearly perpendicular to the main planetary plane, a feature that had been observed in a few extremely distant objects. It would create a population of objects in resonance with Planet 9's own orbit, locked into configurations where their orbital periods maintain simple integer ratios with the planet's period. Most importantly, the hypothesis made testable predictions. If Planet 9 exists with the properties their model suggested, then as we discover more distant objects through ongoing sky surveys, we should find their orbits clustering in specific, predictable ways. We should find objects in the particular resonances the model predicts. The orientation of the cluster should match the model's expectations. These predictions convert Planet 9 from a speculative possibility into a scientific hypothesis that can be evaluated through observation. The probability calculations were compelling. Batygin and Brown estimated that the observed clustering would occur by chance in only about 3 in 10,000 random configurations. As more objects were discovered with orbits matching the predictions, these odds became even more extreme. By traditional scientific standards, a probability of less than 1 in 370, corresponding to a 3 sigma result, is considered evidence of a real effect. The clustering we observe exceeds this threshold significantly. Of course, statistics alone don't prove existence. They indicate that if the clustering is real and not an artifact of observational bias, something must be causing it, and a massive planet represents the most straightforward explanation. The burden then shifts to testing alternative explanations and to directly detecting the planet itself. But the mathematical foundation was clear. A Neptune mass or super-Earth mass planet on a distant eccentric orbit could produce exactly what we observe. And the probability that this clustering arose without such a planet appears vanishingly small. The beauty of this analysis lies in its specificity. Batygin and Brown didn't merely wave their hands and suggest a planet might exist. They calculated its likely mass, its probable orbital parameters, the regions of sky where it might currently reside. They provided a roadmap for observers, narrowing the search from the entire celestial sphere to specific regions where Planet 9, if it exists, should be detectable with sufficiently powerful telescopes. The mathematics of invisible worlds had spoken, pointing toward a specific gravitational presence in the outer dark. The search for Planet 9 echoes the greatest success story in the history of planetary discovery. The detection of Neptune in 1846 through pure mathematical prediction before any telescope had glimpsed it. Understanding how Neptune was found illuminates both the power and the limitations of using orbital perturbations to infer the existence of unseen worlds. By the early 1800s, astronomers had carefully tracked Uranus, discovered by William Herschel in 1781, for several decades. They had established its orbit with precision, allowing them to predict where Uranus should appear at any given time. But as the years passed, Uranus began to deviate from its predicted position. The deviations were small, mere arc minutes, but they were real and measurable. Uranus was not following the orbit that Newton's laws of motion and gravity predicted when considering only the Sun and the known planets. Two possibilities existed. Either Newton's laws failed at the distances of Uranus, requiring a modification to our understanding of gravity, or some unseen mass was gravitationally perturbing Uranus's orbit. Most astronomers favoured the second explanation. The success of Newtonian mechanics in predicting the motions of all other celestial bodies argued against abandoning it. But what could be perturbing Uranus? The answer, several astronomers independently realised, might be an eighth planet, one orbiting beyond Uranus, too faint to have been noticed by casual observers. If such a planet existed, its gravitational pull on Uranus would cause exactly the kind of deviations that were being observed. Moreover, by carefully analysing those deviations, by determining when Uranus moved ahead of its predicted position and when it lagged behind, one could in principle calculate where the perturbing planet must be located. In France, mathematician Urbain Le Verrier undertook this calculation. In England, John Couch Adams performed similar work. Both mathematicians solved the inverse problem. Given the observed perturbations of Uranus, where must an unknown planet be located to produce those effects? The calculations required heroic effort, solving complex equations in celestial mechanics, accounting for the changing positions of multiple planets, working backward from effects to cause. In September 1846, Le Verrier sent his predictions to Johann Galle at the Berlin Observatory. Galle received the letter on September the 23rd, and that very night pointed his telescope to the predicted position. Within 1 degree of Le Verrier's prediction, within the first hour of searching, Galle found Neptune. the planet was exactly where the mathematics said it should be. It was a triumph of theoretical astronomy, proof that human reason and calculation could reveal worlds never before seen. This success inspired searches for additional planets. When Neptune itself showed slight, unexplained perturbations, and when Uranus's orbit still wasn't perfectly explained, even accounting for Neptune, some astronomers proposed a ninth planet, often called Planet X. Percival Lowell dedicated years to this search in the early 1900s, calculating possible positions and conducting photographic surveys. In 1930, Clyde Tombaugh at Lowell Observatory discovered Pluto. Initially, Pluto seemed to validate the Planet X hypothesis. Here was a ninth planet beyond Neptune, found through deliberate search in a predicted region of sky. But as decades passed and Pluto's properties became clearer, problems emerged. Pluto was far too small, too lacking in mass, to produce the perturbations that had motivated the search. When the Voyager 2 spacecraft flew past Neptune in 1989 and refined our measurement of Neptune's mass, the supposed perturbations of Uranus disappeared entirely. They had been artifacts of incorrect mass estimates. Pluto's discovery, it turned out, had been a fortuitous accident, not a confirmation of the Planet X hypothesis. This history teaches important lessons for the search for Planet 9. It demonstrates that orbital perturbations can indeed reveal unseen planets, validating the method's fundamental soundness. Neptune stands as proof that mathematical prediction can locate worlds before telescopes find them. But the story of Pluto reminds us that coincidences occur, that we must be cautious about confirmation bias, that even compelling theoretical arguments require direct observational validation. The case for Planet 9 rests on much more extensive data than the case for Neptune did. Where Leverrier and Adams worked with the orbit of a single planet, modern astronomers examine the correlated behaviour of dozens of distant objects. Where 19th century mathematics relied on hand calculations and approximations, today's researchers run detailed computer simulations modelling millions of years of orbital evolution. The observational basis is broader, the statistical analysis more sophisticated, the alternative explanations more thoroughly examined. Yet uncertainty remains. Until we actually detect Planet 9, until a telescope captures photons that travelled across the outer solar system from this distant world, we cannot be absolutely certain it exists. The mathematical case is compelling, perhaps more compelling than it ever was for the planet that became Neptune, but mathematics alone cannot substitute for direct observation. We search with the confidence that comes from history's successes, tempered by the humility that history's false alarms inspire. Somewhere in the darkness, perhaps a planet waits to vindicate the mathematics once more. To understand how Planet 9 might organise the orbits of distant objects without ever approaching them closely, we need to explore the concept of gravitational shepherding, a phenomenon well documented in other contexts throughout the solar system. Massive planets don't merely pull on nearby objects through close encounters, they reshape entire populations of smaller bodies through long-range gravitational influence operating over immense timescales. The clearest example of shepherding exists in the asteroid belt between Mars and Jupiter. When we examine the distribution of asteroids in this region, we don't find a uniform population. Instead, we discover gaps, regions conspicuously devoid of asteroids at specific distances from the Sun. These gaps, called Kirkwood gaps after their discoverer, appear at locations where an asteroid would have an orbital period in simple ratio to Jupiter's period. An asteroid orbiting at a distance where it completes 3 orbits for every 1 Jupiter orbit, or 5 orbits for every 2 Jupiter orbits, finds itself in what's called a resonance. Resonances might seem like they should be stable, preferred locations. After all, the asteroid and Jupiter return to the same relative configuration repeatedly, establishing a regular pattern. But orbital mechanics is subtle. These repeated configurations mean the gravitational tugs Jupiter exerts on the asteroid occur at the same point in the asteroid's orbit again and again, reinforcing rather than cancelling. Over millions of orbits, these reinforcing tugs add up, gradually changing the asteroid's orbit, typically increasing its eccentricity until the orbit becomes so elliptical that the asteroid encounters Mars or Earth and gets ejected from the region entirely. The result is that resonances act as clearing mechanisms. Asteroids that wander into resonant locations gradually get removed, creating the observed gaps. Jupiter, through its gravitational influence alone, has organized the asteroid belt, carving structure into what might otherwise be a more uniform distribution. This is shepherding in action, a massive planet imposing order on a population of smaller objects through nothing more than the patient accumulation of gravitational effects over cosmic timescales. We see shepherding even more dramatically in Saturn's ring system. The beautiful gaps in Saturn's rings, the distinct boundaries between different ring sections, arise primarily through the gravitational influence of Saturn's moons. Moons like Mimas and Enceladus create resonances at specific distances from Saturn, and ring particles at those distances get perturbed into different orbits, opening gaps. Some moons orbit directly within the rings, creating narrow divisions through their gravitational wake. Pandora and Prometheus, two small moons flanking Saturn's F ring, actively shepherd ring particles, confining them to a narrow band through their combined gravitational effects. Neptune provides perhaps the best analogy for how Planet 9 might work. Neptune has captured Pluto and thousands of other objects into a 3-2 resonance, meaning these objects complete 2 orbits around the Sun for every 3 Neptune completes. This resonance is stable, protecting Pluto from close approaches to Neptune despite Pluto's orbit crossing Neptune's orbital distance. Neptune's gravity has gathered a substantial population of objects into this configuration, creating what we call the Plutinos, a whole family of resonantly trapped objects. Neptune also influences objects well beyond its orbit through secular resonances, slow precessions of orbital elements that can lock objects into correlated configurations. These secular effects operate over millions of years, gradually shepherding objects into specific orbital alignments, even though Neptune never approaches them. The outer edge of the classical Kuiper belt, around 50 astronomical units, appears to be defined by such a secular resonance with Neptune. If Planet 9 exists, it would shepherd distant objects through similar mechanisms. The planet's gravity, though weak at distances of hundreds of astronomical units, would still exert forces on objects with orbital periods of thousands of years. Over millions of years, over thousands of orbits, these forces would accumulate. Objects would gradually drift into or out of resonances with Planet 9. Their orbital planes would precess, tilting in response to the planet's gravitational torques. The orientation of their orbits in space would evolve, influenced by the persistent tug from this distant massive world. The mathematics predicts specific outcomes. Some objects would be shepherded into alignment, their perihelia clustering in the same region of space as Planet 9's perihelion, or directly opposite to it. Other objects would be kicked into highly tilted orbits, their planes nearly perpendicular to the main planetary plane. Still others would be captured into mean motion resonances, maintaining fixed relationships between their orbital period and Planet 9's. What makes the Planet 9 hypothesis compelling is that all these predicted effects match what we actually observe in the outer solar system. The clustering is there, the highly tilted orbits exist, objects in potential resonances have been found. The shepherding effect, demonstrated clearly by Jupiter, Saturn and Neptune in their respective domains, appears to be at work in the outermost solar system as well, organized by a shepherd we have not yet seen, but whose influence appears written in the orbits of the objects it guides. To appreciate why Planet 9 became a serious hypothesis rather than mere speculation, we need to meet the specific objects whose strange orbits forced astronomers to consider explanations beyond chance and observation bias. These are the detached objects, worlds whose orbits carry them so far from the Sun that they rarely, if ever, interact with Neptune or any other known planet, yet whose orbital configurations suggest they've been influenced by something massive. Sedna stands as the founding member of this peculiar population, discovered in November 2003 by a team led by Michael Brown using the Samuel Oschin telescope at Palomar Observatory. Sedna is large for a trans-Neptunian object, roughly 1,000 kilometers in diameter, big enough that its own gravity has pulled it into a nearly spherical shape. But Sedna's size wasn't what made it remarkable. Its orbit was unlike anything previously known in the solar system. Sedna never approaches the Sun closer than 76 astronomical units, more than twice Neptune's distance. At its most distant, Sedna reaches 937 astronomical units from the Sun, nearly into the inner edge of the Oort cloud, that vast spherical shell of comets surrounding the solar system. One orbit takes Sedna approximately 11,400 years. More problematic than these extreme numbers was the fact that Sedna's perihelion, its point of closest approach, lies well beyond the region where Neptune's gravity could have placed it through any plausible scattering process. For an object to reach such a detached orbit, something must have lifted its perihelion away from the realm of planetary influence. A close passage by Neptune could fling an object outward, but such an encounter would typically leave the perihelion near Neptune's orbit, not 76 astronomical units away. One possibility was that a passing star, coming within a light year or so of the Sun billions of years ago, gravitationally perturbed Sedna's orbit. Another was that Sedna formed in the outer solar system and was lifted into its current orbit during the early era, when the Sun still resided in its birth cluster, surrounded by other young stars. For years, Sedna stood alone, a single peculiar object that could be explained away as an outlier, perhaps shaped by rare early conditions that no longer operate. But in 2012, Trujillo and Shepard discovered 2012 VP113, another object on a Sedna-like orbit. Its perihelion was 80 astronomical units, its aphelion about 452 astronomical units, its orbital period around 4,300 years. Here was a second detached object with similar orbital characteristics to Sedna, raising the question of whether we were seeing a pattern rather than isolated anomalies. As observational surveys improved and more sky area was systematically searched, additional detached objects emerged. In 2014-2013, FT28 was announced, with a perihelion of 88 astronomical units. In 2015, V7104 was discovered, potentially even more distant than Sedna at aphelion. In 2018-2015, TG387, nicknamed the Goblin for its discovery near Halloween, was found with a perihelion of 65 astronomical units and an aphelion estimated around 2,300 astronomical units. Each new discovery added to the evidence. When Trujillo and Shepard examined the orbital arguments of perihelion for these detached objects, they found that these parameters clustered within a relatively narrow range. The statistical probability of this clustering arising by chance was low. Something seemed to be organizing these orbits, aligning them in space in a way that demanded explanation. The objects themselves are faint and difficult to observe. Most detached objects are discovered only near perihelion when they're closest to the Sun and reflecting the most sunlight. Even then, they're barely visible in the largest telescopes, appearing as faint points of light moving slowly against the background stars. Their orbits must be determined through painstaking observation over months or years, tracking their motion with sufficient precision to calculate the ellipse they follow. Observational bias complicates the interpretation. Surveys tend to search in the ecliptic plane, where most solar system objects orbit. They favour regions of sky opposite the Sun, where darkness permits deep imaging. They're limited to the areas of sky they've actually surveyed, leaving large regions unexplored. Could the apparent clustering simply reflect where we've looked rather than a real alignment in space? Batygin and Brown's 2016 analysis addressed this question directly, modelling the expected distribution of discoveries given realistic survey biases. They concluded that the observed clustering exceeded what bias alone could produce. While we've certainly discovered preferentially the objects in certain orbital configurations, the degree of alignment we see appears too strong to explain through selection effects alone. The detached objects whisper their message consistently. Their orbits have been shaped. They bear the gravitational imprint of something massive operating over the billions of years since the solar system formed. Whether that something is a single large planet, a population of smaller objects, a temporary perturbation from the Sun's birth environment, or something else entirely remains uncertain. But these frozen worlds, travelling their lonely paths through the outer darkness, carry evidence of influences we have not yet fully identified, clues written in the mathematics of their motion. Before accepting that Planet 9 exists, responsible scientists must examine alternative explanations for the observed orbital clustering. Several competing hypotheses have been proposed, each attempting to explain the strange orbits of detached objects without invoking an unseen planet. Evaluating these alternatives helps us understand why Planet 9 has emerged as the leading explanation despite the absence of direct detection. The most straightforward alternative is observational bias. Perhaps the clustering we see isn't real, but merely reflects where and how we've searched for distant objects. Surveys preferentially search certain regions of sky, particularly along the ecliptic plane and in areas opposite the Sun. If we've only looked in limited directions, we might naturally find objects clustered in those directions, creating an illusion of alignment that would disappear once we surveyed more sky. Several studies have examined this possibility carefully, simulating what we should observe given realistic survey coverage and detection efficiencies. These simulations suggest that while bias certainly affects which objects we discover, the degree of clustering we observe exceeds what bias alone would predict. The objects we've found are more aligned than they should be, even accounting for where we've looked. This doesn't eliminate bias as a contributing factor, but it suggests bias cannot fully explain the observations. A more sophisticated alternative involves the self-gravity of the Kuiper belt itself. If the belt contains more total mass than current estimates suggest, perhaps distributed in many small objects we haven't yet detected, the collective gravitational influence of this mass might create the observed clustering. Computer simulations exploring this idea show that under certain conditions, a massive extended disk could produce some alignment through gravitational interactions among its constituent objects. However, the mass required appears problematically large, perhaps several Earth masses spread across the outer solar system. Current observations limit the total mass of the Kuiper belt to only a small fraction of an Earth mass. To hide multiple Earth masses would require either an enormous population of small objects below current detection limits, or a population of Mars-to-Earth mass objects that somehow have eluded detection despite extensive surveys. While not impossible, this explanation seems to require more hidden mass than the single Planet 9 hypothesis. Another alternative proposes that a star passed close to the Sun in the distant past, perhaps 3 or 4 billion years ago, gravitationally perturbing the orbits of outer solar system objects. Such an encounter could indeed create detached objects with aligned orbits, lifting their perihelia away from Neptune while organizing their orientations through the star's gravitational influence during its passage. This idea has some merit. The Sun formed in a cluster of stars and likely experienced close encounters during its first few 100 million years. Stellar dynamics suggests occasional, closer passages might occur even after the Sun left its birth cluster. The problem is timing and stability. Computer simulations indicate that the specific alignment we observe today would require a stellar encounter with very particular properties occurring at a specific time. Moreover, the alignment produced by such an encounter should gradually decay over billions of years due to differential precession. The fact that we see strong clustering today seems difficult to reconcile with a one-time perturbation billions of years ago. A more exotic alternative emerged in 2019 when some physicists suggested Planet 9 might not be a planet at all, but rather a primordial black hole, a hypothetical type of black hole formed in the early universe rather than from stellar collapse. A black hole with the mass of several Earths would be incredibly small, perhaps the size of a grapefruit, making it even more difficult to detect than a faint planet. It would still exert the same gravitational influence, producing the observed orbital clustering. This hypothesis is intriguing, but faces significant challenges. Primordial black holes remain hypothetical, with no confirmed examples observed anywhere. The probability that one would happen to be orbiting our Sun seems extraordinarily low. Moreover, as such a black hole moved through the Kuiper belt, it should occasionally pass close enough to smaller objects to accrete material or produce detectable radiation signatures, effects that have not been observed. The black hole hypothesis can't be entirely ruled out, but it seems to multiply mysteries rather than resolving them. Occam's razor, the principle that simpler explanations should be preferred when multiple explanations fit the observations, tends to favor Planet 9. A single planet with reasonable mass and orbital properties can explain the full range of observations. The clustering of orbital arguments of perihelion, the tilted orbits, the specific resonances, the distribution of orbital eccentricities. Alternative explanations typically require either special circumstances, hidden mass distributions, or exotic objects, each adding complexity without necessarily fitting the data better. This doesn't prove Planet 9 exists. Science doesn't work through proof of existence, but through accumulation of evidence and elimination of alternatives. What we can say is that among current explanations for the observed orbital architecture of the outer solar system, a Neptune-mass planet on a distant eccentric orbit provides the simplest account, consistent with all available data. The hypothesis makes testable predictions. It explains multiple phenomena with a single cause. It invokes only known physics and reasonable conditions. Until we detect Planet 9 directly, uncertainty remains. But the alternatives examined so far seem less probable, less comprehensive, or more contrived than the straightforward proposition that a large planet orbits in the outer solar system, hidden simply by distance and faintness, waiting to be found. If Planet 9 exists, current evidence suggests it is what astronomers call a super-Earth, a planet more massive than Earth, but less massive than Neptune or Uranus. This places it in a category of planet that is extremely common throughout the galaxy, but absent from the inner regions of our own solar system, an ironic gap that Planet 9 would fill if it proves real. The estimated mass of Planet 9 ranges from 5 to 10 Earth masses, with most models favouring values near the lower end of this range. This makes it roughly similar to the ice giants Uranus and Neptune, which weigh in at 14.5 and 17 Earth masses respectively, though Planet 9 would be somewhat less massive. The mass estimate comes from the strength of the orbital perturbations needed to produce the observed clustering, combined with assumptions about the orbital parameters. A more massive planet would produce stronger effects, allowing it to be farther away or on a less optimal orbit, while a less massive planet must be closer or better positioned to create the same observable signatures. Super-Earths represent the most common type of exoplanet discovered in surveys of other stars. Planets with masses between 2 and 10 Earth masses appear frequently around Sun-like stars, outnumbering both smaller Earth-like worlds and larger Neptunes in many surveys. These planets occupy a mass range between terrestrial planets like Earth and ice giants like Neptune, and their internal structure can vary considerably depending on their composition and formation history. The prevalence of super-Earths elsewhere makes their absence in our own solar system somewhat puzzling. The 8 planets we've known for centuries include 4 terrestrial worlds, with Mars being the largest at 0.1 Earth masses, and Earth itself at 1 Earth mass, then a gap, then 4 giant planets, with Neptune being the smallest at 17 Earth masses. Nothing exists in the 1 to 17 Earth mass range in the inner solar system. If Planet 9 exists at 5 to 10 Earth masses, it would partially fill this gap, though its location in the outer solar system means it's not quite the same as the super-Earths found close to other stars. The mass of Planet 9 has profound implications for its nature and properties. A planet in this mass range is large enough that its gravity would have pulled it into a spherical shape, overcoming any structural strength of rock or ice. It would be large enough to retain an atmosphere, possibly a thick hydrogen-helium envelope if it formed in the outer solar system, or a substantial atmosphere of heavier volatiles if it's more rocky. Its internal heat, generated by the slow contraction of the planet and the decay of radioactive elements, might still drive geological activity even after 4.5 billion years. Comparing Planet 9 to Neptune and Uranus provides some insight into what it might be like. Those ice giants are not actually made primarily of ice in the everyday sense, but rather consist of water, methane, and ammonia in various phases surrounding a rocky core. Their masses are dominated by these ices, which at the temperatures and pressures in planetary interiors behave more like dense fluids than frozen solids. Neptune and Uranus likely have cores of rock and metal with masses of a few Earth masses, surrounded by mantles of compressed ices and capped by thick atmospheres of hydrogen and helium. Planet 9, if it resembles a scaled-down ice giant, might have similar composition. A rocky core, perhaps 2 or 3 Earth masses, surrounded by a mantle of water, methane and ammonia, perhaps 3 to 5 Earth masses, topped by an atmosphere that could be substantial or minimal depending on how the planet formed and how much volatile material it retained. The planet's lower mass compared to Neptune means its interior pressures would be lower, affecting the phases and properties of its constituent materials. Alternatively, Planet 9 might be more like a giant terrestrial planet, a rocky super-Earth with a composition dominated by rock and metal rather than ices and gases. Such planets are thought to form in the inner regions of planetary systems where temperatures are higher, but if Planet 9 formed closer to the Sun and was later ejected outward, it might have this composition. A rocky Planet 9 would be denser than an icy one, with different internal structure and perhaps different atmospheric properties. The distinction matters because it relates to formation scenarios. An icy super-Earth likely formed in the outer solar system where ices could condense, perhaps in the region between Jupiter and Neptune, before being scattered outward. A rocky super-Earth would have formed farther in, possibly in the terrestrial planet region, requiring a more violent ejection process to reach its current distant orbit. Each scenario has different implications for the early history of the solar system and for the likelihood that Planet 9 exists where models suggest. Whatever its composition, Planet 9's mass makes it substantial. This is not a dwarf planet like Pluto, not an overgrown asteroid, but a genuine world, one that would rank among the largest planets in the solar system if it could be included in the traditional count. Its gravity would be strong enough to hold moons, to shape rings, to influence a substantial region of space around it. If we could stand on its surface, we would feel significant gravity, perhaps half of Earth's if it's icy and extended, or closer to Earth's if it's rocky and compact. We would be standing on a world whose mass reflects a substantial fraction of the material that once existed in the outer solar system. a world whose existence would reshape our understanding of how planets form and migrate. Planet 9's orbit, if current models are correct, is unlike any other planet's orbit in the solar system. It's an extreme ellipse, stretched and tilted, carrying the planet from relative proximity to Neptune's realm out to distances where the Sun's influence weakens to nearly nothing. Understanding this orbit is essential to grasping both why Planet 9 remains so difficult to find and what its existence would tell us about solar system history. The semi-major axis of Planet 9's orbit, the average of its closest and farthest distances from the Sun, is estimated at between 400 and 800 astronomical units, with most models favouring values around 500 to 600 astronomical units. For comparison, Neptune orbits at 30 astronomical units. Earth orbits at 1 astronomical unit. Planet 9's average distance from the Sun is roughly 15 to 20 times farther than Neptune, placing it in a realm where even the Sun's gravitational dominance begins to weaken. The orbital period corresponding to these distances is immense. Kepler's third law relates orbital period to semi-major axis, and for a semi-major axis of 500 astronomical units, the period works out to approximately 10,000 to 15,000 Earth years. Some models suggest even longer periods, potentially 20,000 years. This means Planet 9 has completed only a few hundred orbits since the solar system formed 4.5 billion years ago. It moves slowly, creeping along its path at average speeds of only a few kilometers per second compared to Earth's 30 kilometers per second. The orbit's eccentricity measures how elongated it is, with 0 representing a perfect circle and values approaching 1 representing increasingly stretched ellipses. Planet 9's eccentricity is estimated between 0.2 and 0.5, meaning its orbit is significantly elliptical. This eccentricity means Planet 9's distance from the Sun varies dramatically over the course of its orbit. At perihelion, its closest approach, Planet 9 might come within 200 to 300 astronomical units of the Sun. At aphelion, its farthest point, it could reach 800 to some 200 astronomical units, or even more. This variation has crucial implications for detection efforts. If Planet 9 is currently near aphelion, as some analyses suggest it might be, it would be at its faintest, reflecting minimal sunlight from its maximum distance. Telescopes might struggle to detect it even if they looked directly at it. Conversely, if it's near perihelion, it would be substantially brighter, perhaps bright enough for existing surveys to have already found it, if it weren't in a particularly difficult region of sky like the galactic plane where background stars create confusion. The orbit's inclination, the angle at which it tilts relative to the main planetary plane, adds another layer of complexity. Estimates suggest Planet 9's orbit is tilted between 15 and 30 degrees relative to the ecliptic, the plane in which Earth and most planets orbit. This inclination means Planet 9 spends much of its time above or below the zodiac band, where most solar system objects are found, and where most surveys concentrate their search efforts. The orientation of Planet 9's orbit in space, defined by parameters like the argument of perihelion and the longitude of ascending node, determines where in the sky the planet appears at any given time. Current models constrain these parameters somewhat, based on the requirement that the planet's gravitational influence explains the observed clustering of detached objects. These constraints point to specific regions of sky, but those regions remain large enough to require years of systematic searching. Taken together, Planet 9's orbital parameters place it in a uniquely challenging location for detection. It's distant, making it faint. It moves slowly, making it hard to distinguish from background stars without multiple observations spaced over time. Its orbit is tilted, taking it out of the most thoroughly surveyed portions of sky, and it might currently be near aphelion, at its most distant and faintest. These factors explain why, despite years of dedicated searching with powerful telescopes, Planet 9 remains elusive. The orbit's shape raises important questions about formation and evolution. Planets don't naturally form on such eccentric orbits. The protoplanetary disk from which planets condensed was relatively thin and circular. Planets forming within it should have nearly circular orbits in the disk plane. Planet 9's eccentric and tilted orbit therefore demands an explanation. One possibility is that Planet 9 formed on a more circular orbit closer to the other planets and was later ejected to its current orbit through gravitational scattering. Perhaps during the early solar system's chaotic phase, when planets were migrating and interacting strongly, Planet 9 had a close encounter with Jupiter or Saturn that flung it outward. The encounter would increase both the orbit's semi-major axis and its eccentricity, potentially also tilting it relative to the original disk plane. Another possibility is that Planet 9 formed in the outer solar system, perhaps between Neptune and the Kuiper belt, and was gradually perturbed to its current orbit through multiple weak interactions rather than a single dramatic encounter. This scenario might produce less extreme eccentricity, but could still result in the elongated orbit we infer. A third scenario proposes that Planet 9 didn't form around our Sun at all, but was captured from another star early in the solar system's history, when the Sun still resided in its birth cluster. Captured planets would naturally have eccentric, tilted orbits, as their capture involves a complex three-body interaction between the planet, its original star, and the Sun. This scenario is statistically unlikely, but not impossible, and it would explain Planet 9's orbital peculiarities naturally. Each formation scenario has different implications for Planet 9's composition, its current orbital properties, and the likelihood that we'll find it. The orbit itself, however it arose, remains one of the key pieces of evidence for the planet's existence and one of the primary obstacles to its detection. The question of Planet 9's origin is intimately connected to the broader story of how our solar system formed and evolved over its 4.5 billion year history. If Planet 9 exists, understanding where it came from helps us reconstruct the dramatic events that shaped the planetary architecture we see today. Three main scenarios have been proposed, each with different implications and different probabilities. The first scenario suggests Planet 9 formed in the outer region of the solar system, perhaps originally orbiting between 15 and 30 astronomical units from the Sun, in the same general region where Uranus and Neptune now reside. In this picture, the early solar system contained more giant planet cores than the four we see today. These cores competed for the available gas and ice in the protoplanetary disk, growing through accretion of solid material and gravitational capture of gas. During this formation phase, the giant planets interacted gravitationally with each other and with the remaining disk of small bodies. These interactions caused the planets to migrate, changing their orbital distances over millions of years. Some migration occurred smoothly as planets exchanged angular momentum with the disk. Other migration came through more violent scattering events, where close approaches between planets resulted in dramatic changes to their orbits. Computer simulations of this era suggest that Jupiter and Saturn, as the most massive planets, dominated these interactions. If a fifth giant core existed, one that grew to several Earth masses but not to Neptune's full size before the gas in the disk dissipated, this planet could have been scattered outward through an encounter with Jupiter or Saturn. A single close passage could boost its orbital energy dramatically, flinging it into the outer solar system on an eccentric orbit. The ejection hypothesis explains several features of Planet 9's inferred properties. It accounts for the eccentric orbit. It explains why the planet's mass is less than Neptune's, as it would have had less time to accrete gas before being ejected. It provides a natural formation location where ice and rock were abundant, and it connects to the broader narrative of early solar system violence that explains features like the NICE model, which describes the migration of the giant planets and its effects on the outer solar system. However, ejection scenarios face challenges. Getting a planet all the way to 500 or 600 astronomical units through planetary scattering is difficult. Most planets that get ejected either escape the solar system entirely, becoming rogue planets, drifting through interstellar space, or end up on less extreme orbits. The ejected planet would also need to avoid being perturbed again by subsequent encounters or by interactions with the remaining disk material. The second scenario proposes that Planet 9 formed in the outer solar system, perhaps beyond 100 astronomical units, from the disk of material that also formed the Kuiper belt. In this picture, Planet 9 is essentially a Kuiper belt object that grew much larger than the others, accumulating enough mass to dominate its formation region. This scenario requires special conditions, perhaps a local concentration of material or an extended period of formation time, to allow such a large planet to grow so far from the Sun, where disk densities were low and formation timescales were long. This formation-in-place scenario struggles to explain Planet 9's eccentric orbit. Objects forming in a disk naturally have nearly circular orbits aligned with the disk plane. To produce the eccentricity and inclination Planet 9 displays would require subsequent perturbations, perhaps from passing stars during the Sun's early cluster phase, or from gravitational interactions with other massive Kuiper belt objects that have since been ejected or scattered into different orbits. The third scenario is perhaps the most exotic. Planet 9 might not have formed in our solar system at all, but around another star, and was later captured during the Sun's early history when it resided in a cluster of newborn stars. Stellar clusters are dense environments where stars pass relatively close to each other. If the Sun passed within a few hundred astronomical units of another star, and if that star had a planet on a distant orbit, the complex three-body gravitational interaction could potentially result in the planet transferring from one star to the other. Capture scenarios naturally produce eccentric, tilted orbits, as the captured planet's motion reflects the chaotic dynamics of its capture rather than the ordered formation process in a protoplanetary disk. Capture also potentially explains why Planet 9's composition might differ from what we'd expect for an object formed at its current location. If it formed around a different star with different formation conditions, it might have properties that seem anomalous for our solar system. The probability of capture, however, is extremely low. The geometry and timing must be precise. The Sun must pass close enough to another star. That star must have a suitably positioned planet, and the encounter must result in capture rather than ejection or no interaction. Statistical studies suggest that even in dense stellar clusters, the probability of any given star capturing a planet is only a small percentage. The odds that our Sun specifically captured a planet of the right mass in the right orbit seem vanishingly small. Recent work has explored hybrid scenarios, attempting to combine elements of different formation mechanisms. Perhaps Planet 9 formed in our solar system, but its orbit was strongly perturbed by a close stellar encounter that occurred after formation, but early enough to affect the planet's trajectory significantly. Or perhaps Planet 9 formed through core accretion in the outer solar system, but interacted with a massive disk of small bodies that has since dispersed, with those interactions pumping up the planet's eccentricity and inclination. Each scenario makes different predictions about Planet 9's composition, its orbital properties, and the likelihood of finding other similar objects in the outer solar system. Distinguishing between these scenarios will require actually detecting Planet 9 and measuring its properties directly. Its composition, particularly the ratio of rock to ice and the presence or absence of a substantial atmosphere, would provide strong clues about formation location. Its exact orbital parameters, refined beyond current estimates, would constrain the scattering or capture dynamics. The question of Planet Nine's origin thus connects to fundamental questions about planetary system formation and evolution. Did our solar system form peacefully, with planets in roughly their current positions, or did it experience dramatic upheaval with planets migrating, scattering, and perhaps being ejected? Is our solar system's architecture typical or unusual? Understanding Planet Nine's history would illuminate these broader questions, adding another chapter to the story of how a disk of dust and gas surrounding a young star becomes a family of worlds. Imagine you could travel across the solar system, beyond Neptune's blue atmosphere, beyond Pluto's icy plains, out into the darkness where the sun shrinks to a brilliant point of light. You journey for years at impossible speeds, crossing hundreds of astronomical units, until finally, ahead in the blackness, you discern a world, Planet 9, the ghost in the outer dark made tangible. What would you see? The first thing you'd notice is how faint the sun appears. At 500 astronomical units, the sun shines with about 1,050,000th the brightness we experience on Earth. It's still by far the brightest object in the sky, brighter than any planet or star, bright enough to cast shadows and provide illumination roughly 50 times more intense than the full moon does on Earth. But it's clearly a point source, no longer a disk, a piercing diamond of light against the black. Planet 9 itself would appear dark, but not completely black. If it has a reflective, ice-rich surface like Neptune or Uranus, it might reflect a small fraction of the sunlight reaching it, giving it a faint glow. The surface temperature would be extraordinarily cold, perhaps 40 to 50 Kelvin. Cold enough that most substances we think of as gases on Earth exist as frozen solids. Nitrogen would be ice, methane would be ice, even carbon dioxide would be frozen solid at these temperatures. But Planet 9 might not be entirely cold. Like other massive planets, it likely retains internal heat from its formation. The gravitational potential energy released as the planet accumulated, converting to thermal energy. Radioactive decay of elements like uranium, thorium, and potassium in any rocky core would add additional heat over billions of years. This internal heat, though small, might maintain liquid layers beneath an icy surface, similar to how Jupiter's moon. Europa maintains an ocean beneath its ice shell despite being far from the sun. If Planet 9 is an ice giant like a smaller Neptune, its atmosphere might consist primarily of hydrogen and helium, left over from the planet's formation in the protoplanetary disk. Below this gaseous envelope would be a mantle of compressed ices, water, methane and ammonia in fluid or solid phases, surrounding a core of rock and metal. The planet might have bands of clouds in its atmosphere, though they'd be incredibly faint and difficult to observe from Earth. Atmospheric circulation driven by internal heat could create weather patterns, storms that last for years or decades. The colour of Planet 9 is uncertain, but could be striking. Neptune and Uranus both appear blue due to methane in their atmospheres, absorbing red wavelengths. If Planet 9 has similar composition, it too might be blue, though in the faint sunlight colour would be muted. Alternatively, if organic compounds called tholins form in its upper atmosphere from the breakdown of methane by cosmic rays and ultraviolet light, the planet might have a reddish or tan hue, similar to Titan's atmosphere. If Planet 9 is more rocky than icy, its appearance would be different. A super-Earth with composition dominated by rock and metal might have a thinner atmosphere, or even be essentially airless if it lost its primordial gas envelope. The surface might be cratered like the Moon, marked by billions of years of impacts from comets and debris. Without active geology to erase them, these craters would accumulate, recording the planet's impact history across the age of the solar system. The sky from Planet 9 would be remarkable. The sun would appear as a brilliant white star, distinctly brighter than anything else but not dominating the heavens. Venus might be visible near the sun. The brightest planet as seen from Earth would be the brightest planet as seen from Planet 9 as well, though far fainter. Jupiter and Saturn might be barely detectable, points of light requiring careful observation to distinguish from background stars. But the stars themselves would be the main feature of Planet 9's sky, with minimal atmosphere to scatter light and no bright sun to create a blue sky. The stars would be visible at all times, sharp and steady, not twinkling as they do through Earth's turbulent atmosphere. The Milky Way would arch across the sky in stunning detail, billions of stars creating a river of light. The constellations would look identical to how we see them from Earth, as Planet 9's orbital motion is tiny compared to interstellar distances. If Planet 9 has moons, and it very likely would, they would add drama to the sky. Moons could have formed during the planet's accretion from the circumplanetary disk of material that surrounded the growing planet. Alternatively, Planet 9 might have captured passing objects, pulling them into orbit through gravitational interactions. These moons would orbit the planet relatively quickly, compared to the planet's years-long orbital period, creating phases and eclipses, passing in front of the distant sun, casting shadows on the planet below. The surface, if we imagine standing on it, would be alien, beyond almost any other place in the solar system. The gravity might be substantial, perhaps half Earth's, or more depending on the planet's size and density. The ground beneath your feet could be water ice mixed with rock, or perhaps nitrogen ice, if surface temperatures allow it to remain solid. The horizon would curve away more gradually than on Earth if the planet is larger in radius, extending the visible distance. Time would feel strange on Planet 9. A day, the planet's rotation period, would depend on how fast the planet spins. If it's similar to Neptune, a day might last about 16 hours, but the year, the orbital period, would be incomprehensibly long, 10,000 to 20,000 Earth years. Generations could live and die without seeing any perceptible motion in the planet's position relative to the background stars, without any change in the seasons or the sun's brightness. This is the world that might be waiting in the outer darkness, a planet of ice and rock and gas, cold and distant, nearly invisible from Earth, but substantial, real, a member of our solar family that we have not yet met. If Planet 9 exists, it almost certainly does not orbit alone. The physics of planet formation and the dynamics of the outer solar system suggest strongly that Planet 9 would have accumulated a system of moons and possibly rings as well, creating a miniature planetary system in the outer dark. Understanding what these satellites might be like gives us another window into Planet 9's nature and history. Every large planet in our solar system has moons. Earth has one, Mars has two, and the giant planets have extensive systems. Jupiter has at least 79 known moons, Saturn 82, Uranus 27, and Neptune 14. These numbers keep growing as improved telescopes detect smaller and more distant satellites. The prevalence of moons around all large planets suggests that moon formation is a natural consequence of planetary formation and evolution. Moons form through several mechanisms. Regular satellites, those on nearly circular orbits aligned with their planet's equator, typically form from the circumplanetary disk of material that surrounds a growing planet. As the planet accretes mass from the protoplanetary disk, a portion of that material enters orbit around the planet, rather than falling directly onto it, forming a disk that rotates with the planet. Within this disk, the same processes that form planets from the solar nebula operate on a smaller scale, with collisions building larger objects from smaller ones. If Planet 9 formed through core accretion in the outer solar system, it would have had such a circumplanetary disk during its growth phase. Moons forming in this disk would be relatively large, on circular orbits close to the planet's equatorial plane. They might be icy worlds given the composition of the material available in the outer solar system, possibly similar to Saturn's large moons like Titan or Enceladus, though smaller given Planet 9's smaller mass. The size distribution of these regular moons would depend on Planet 9's mass and the extent of its circumplanetary disk. More massive planets can retain larger disks and form larger moons. If Planet 9 is at the lower end of mass estimates, perhaps 5 Earth masses, its largest moon might be a few hundred kilometers in diameter. If it's more massive, approaching 10 Earth masses, it might have moons rivaling or exceeding the size of our own moon. Irregular satellites, in contrast, are captured objects on eccentric, often tilted, orbits at large distances from their planet. Neptune's largest moon, Triton, is almost certainly a captured Kuiper Belt object, given its retrograde orbit and large size. Most of Jupiter's and Saturn's moons are small, captured objects, likely asteroids or comets gravitationally snared as they passed near the planet. Planet 9, moving through the outer solar system on its eccentric orbit, would periodically pass through regions populated by Kuiper Belt objects and scattered disk objects. During these passages, it might capture objects into orbit through several mechanisms. If the planet has an extended atmosphere, or if an object passes through a debris disk around the planet, drag forces could remove enough energy to bind the object into orbit. Three-body interactions involving the Sun, Planet 9, and a passing object could occasionally result in capture. The total number of moons Planet 9 possesses would depend on its entire history, how it formed, whether it was ejected from the inner solar system or formed in place, how many close encounters with other planets or debris fields it experienced. A planet that formed in the outer solar system and remained relatively undisturbed might have primarily regular satellites from its formation disk. A planet that was scattered through the Kuiper Belt might have captured numerous irregular satellites. Beyond moons, Planet 9 might have rings. All 4 giant planets in our solar system have ring systems, though Saturn's are by far the most spectacular. Rings form through several mechanisms: tidal disruption of moons or passing objects that come within the planet's Roche limit, impact ejection of material from moons, or perhaps capture of debris from cometary breakups. Planet 9's rings, if they exist, would be faint and tenuous. The planet's low temperature means ices would be solid and brittle, perhaps making it easier for impacts to shatter satellites and produce ring material. Conversely, the faint sunlight means any ring particles would be extraordinarily dark and difficult to detect from Earth. The rings might be composed primarily of water ice with some rocky material, similar to Saturn's rings, though likely much less dense. The dynamics of Planet 9's satellite system would be fascinating. At such great distances from the Sun's gravitational influence on Planet 9's moons would be weak but not negligible. The moon's orbits would precess slowly under the Sun's perturbations. Tidal interactions between Planet 9 and its moons would gradually circularize their orbits and synchronize their rotation periods, just as our moon is tidally locked to Earth and tidally receding from it. If Planet 9 has multiple large moons, they might interact gravitationally with each other, creating resonances similar to those among Jupiter's Galilean satellites or Saturn's inner moons. These resonances could maintain orbital eccentricities that would otherwise be damped by tides, potentially driving geological activity on the moons through tidal heating, just as tidal heating powers volcanic activity on Jupiter's Io and maintains the subsurface ocean on Europa. The moons themselves could be geologically diverse. Large icy moons might differentiate, with rocky cores surrounded by ice mantles. Internal heat from radioactive decay and tidal forces might maintain subsurface liquid layers, potentially even subsurface oceans. These oceans, if they exist, would be under thick ice shells in complete darkness. But chemical energy from rock-water interactions might support microbial life, a possibility that makes Planet 9's satellite system not just interesting for astronomy, but potentially for astrobiology. From Earth, detecting Planet 9's moons would be extraordinarily challenging. Even if Planet 9 itself is eventually found, resolving separate points of light representing individual moons would require the most powerful telescopes and sophisticated imaging techniques. The moons would be even fainter than the planet, and close to it in the sky, making them difficult to distinguish. Most of what we might learn about Planet 9's satellite system would likely come from theoretical modelling and comparison to the moon systems of known giant planets. Yet these moons, hypothetical though they remain, represent an important part of Planet 9's story. They would be worlds unto themselves, each with unique properties and histories, each contributing to the gravitational complexity of the Planet 9 system. When and if Planet 9 is discovered, understanding its moons will be one of the many exciting frontiers of exploration that follows, another set of mysteries emerging from solving the first mystery of the planet's existence. Let us conduct a thought experiment, a meditation on perspective and scale. Close your eyes for a moment and imagine yourself standing on the surface of Planet 9, that distant hypothetical world at the edge of our solar system. What would the universe look like from this furthest outpost, this boundary between our sun's domain and the darkness beyond? The sun would not dominate your sky as it dominates ours. At 500 astronomical units, the sun subtends an angle of only about 4 arcseconds, far too small for your eye to resolve as a disk. It would appear as a point, an intensely brilliant star, far brighter than anything else in the sky, but unmistakably a star rather than the extended disk we see from Earth. Its brightness would be about 50 times that of the full moon, as seen from Earth, enough to cast noticeable shadows, enough to illuminate the landscape around you in a perpetual dim twilight, but not remotely like the flood of light we enjoy on Earth. This sunlight would be cold comfort. The inverse square law governs how light spreads across space, and at Planet 9's distance, each square meter receives only about 1/150,000th the energy that reaches Earth. This translates to a solar constant, the amount of solar energy per unit area, of about 0.005 watts per square meter at perihelion, even less at aphelion. For comparison, Earth receives about 1,260 watts per square meter. The sun's warmth, so life-giving on Earth, would be barely detectable on Planet 9's surface. The sky itself would be remarkable in its clarity and darkness, with little or no atmosphere to scatter light, or only a thin atmosphere unable to create a bright daytime sky. The stars would be visible constantly, as sharp and unwavering as they appear from the moon. The sun would be the brightest object, but the stars would compete for attention in a way impossible on Earth, where scattered sunlight washes them out during daylight. Looking back toward the inner solar system, you might barely detect some of the planets. Venus, the brightest planet as seen from Earth, would appear as perhaps the second or third brightest star-like point in the sky after the sun, though orders of magnitude dimmer. Jupiter might be visible if you knew where to look, its enormous size compensating somewhat for the vast distance. Mars and Mercury would be lost in the sun's glare. Earth would be invisible, too close to the sun and too small to resolve, a pale blue dot made utterly insignificant by distance. Saturn's rings, that remarkable feature visible even from Earth with modest telescopes, would be impossible to resolve from Planet 9 without extraordinary optical equipment. Saturn would appear as merely a bright star near the sun. Uranus and Neptune, ice giants that already challenge observers from Earth, would be invisible from Planet 9 without telescopic aid, lost among the background stars. The stars themselves would look identical to how we see them from Earth. The distance from Earth to Planet 9, though vast on solar system scales, is negligible compared to even the nearest stars. Alpha Centauri remains 4.37 light-years away, whether measured from Earth or Planet 9. The constellations are unchanged. Orion rises in the same pattern. The Milky Way arches across the sky in the same magnificent sweep. But there would be one potential difference in the stellar view. Proper motion and parallax would be measured against a slightly different baseline. Over the thousands of years comprising Planet 9's orbital period, its motion through space would carry it along an arc hundreds of astronomical units across. The nearest stars would show parallax shifts, apparent movements against background stars, different from those observed from Earth or the Sun. This effect is tiny, but it means the very nearest stars might appear in slightly different positions relative to distant stars, compared to their positions as seen from Earth. If Planet 9 has moons, they would add beauty and interest to your sky. A large moon orbiting at a reasonable distance would appear as a disk, going through phases as it orbits the planet, lit by the distant sun. From the planet's surface, you could watch this moon transit in front of the sun, briefly dimming that brilliant point of light, creating an eclipse, though the sun would remain a point throughout. The length of a day on Planet 9 depends on its rotation period, which we don't know. If it's similar to Neptune's 16-hour rotation, the stars would wheel across the sky at a stately pace, making one complete circuit every 2/3 of an Earth day. The sun would rise and set, though these words lose some meaning when the sun is merely a bright star providing dim illumination. The concept of day and night becomes more about the presence or absence of this particular star above the horizon than about light and dark as we experience them. A year on Planet 9 would be incomprehensibly long. 10,000 Earth years, 15,000, perhaps 20,000. In a single year on this world, human civilizations on Earth would rise and fall. Languages would be born, flourish, and die. Mountains would erode perceptibly. The climate of Earth would cycle through variations. The most ancient trees on Earth live about 5,000 years, meaning 2 or 3 of their entire life cycles would fit within a single orbit of Planet 9. From Planet 9's perspective, the other planets would move in complicated patterns as both they and Planet 9 orbit the Sun. Venus and Mercury would oscillate back and forth near the Sun as their shorter orbital periods carry them around the Sun multiple times during Planet 9's slow crawl along its orbit. Jupiter and Saturn would move more slowly, but still perceptibly, making multiple circuits of the sky over Planet 9's year. The Earth's seasons, its 4 gentle transitions of temperature and daylight, would be utterly alien to Planet 9. If the planet's rotation axis is significantly tilted relative to its orbital plane, seasons would exist, but each would last thousands of Earth years, a summer that spanned the entire recorded history of human civilization. A winter that began before the pyramids were built and ended in our current era. These are timescales that dwarf human experience, that challenge our ability to conceive of change and continuity. This is the perspective Planet 9 would offer, a view of our solar system from its outer edge, a vantage point that would make clear how the system is centered on the Sun, yet how vast the space surrounding the Sun truly is. From Planet 9, you would be a citizen of the solar system, but barely, perched at the boundary, looking inward at our star family and outward toward the greater galaxy beyond. Searching for Planet 9 represents one of the most technically demanding observational challenges in modern astronomy. The planet, if it exists, is extraordinarily faint, moving almost imperceptibly across the sky, hiding somewhere in a search area that covers thousands of square degrees. Understanding why Planet 9 remains elusive, despite years of dedicated effort, requires appreciating the fundamental limitations of telescopes and the vast scale of the search space. The primary challenge is brightness, or rather, the lack of it. Planets shine by reflected sunlight, and the amount of light they reflect depends on their size, their reflectivity, and crucially, their distance from both the Sun and Earth. The intensity of sunlight diminishes with the square of the distance from the Sun, and the light reflected by a planet diminishes again with the square of the distance from the planet to Earth. Combined, this creates a fourth power dependence on distance for objects in the outer solar system. Planet 9 at 500 to 600 astronomical units would receive about 1/150,000th the sunlight that Earth receives. Of that tiny amount, it would reflect some fraction back into space and we would receive about 1/150,000th of that reflected light. The combined effect makes Planet 9 extraordinarily dim, potentially fainter than magnitude 22 or 23, which is about 10 million times fainter than the faintest stars visible to the naked eye. For comparison, Pluto, at its distance of about 40 astronomical units, shines at magnitude 14, already requiring a decent telescope to observe. Neptune at 30 astronomical units is magnitude 8, visible in binoculars, but not to the naked eye. Planet 9 would be roughly 100 times fainter than Pluto and 10,000 times fainter than Neptune. Only the largest telescopes on Earth, using long exposures and sophisticated detectors, can reach the magnitudes necessary to detect Planet 9. But faintness alone doesn't fully capture the difficulty. The sky contains millions of objects at magnitude 22 and fainter, distant galaxies, quasars, background stars in dense regions. Finding Planet 9 requires distinguishing it from these countless background objects. The key is motion. Solar system objects move relative to the background stars due to their orbital motion around the Sun. Over nights and weeks, planets shift position, while distant galaxies remain fixed. Detecting this motion requires multiple observations of the same region of sky, spaced in time, comparing the positions of every object between images. Automated software can identify objects that move, flagging them as potential solar system bodies. But at Planet 9's distance, the angular motion is tiny. In a single night, Planet 9 might move only a few arc seconds, less than the typical resolution of ground-based telescopes without adaptive optics. Over a month, it might move a few arc minutes, comparable to the size of Mars as seen from Earth. This slow motion means you need observations spaced over long periods to clearly establish that an object is moving, rather than just appearing in slightly different positions due to measurement uncertainty. But spacing observations far apart introduces new problems. You need to observe the same field repeatedly, requiring telescope time that could be used for other projects. And you need to account for the object moving out of your field of view. Between observations, if you wait too long, the search area compounds these difficulties. Planet 9's orbit is constrained somewhat by the clustering analysis, but those constraints still leave thousands of square degrees where the planet might be. For comparison, the full moon subtends about half a degree in diameter, or about 0.2 square degrees. The entire visible sky comprises about 20,000 square degrees. Planet 9 could be anywhere, in a region encompassing perhaps 2,000 to 5,000 square degrees, depending on how tightly the models constrain its position. Modern wide-field survey telescopes can image several square degrees per exposure, but reaching the necessary depth to detect magnitude 22 objects requires exposures of tens of minutes. Surveying thousands of square degrees to this depth, multiple times to detect motion, represents years of observing time, even with dedicated facilities. The Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, has surveyed large areas of sky but focuses on regions near the ecliptic. The Zwicky Transient Facility scans much of the northern sky nightly but may not reach the depth necessary for Planet 9 detection in single exposures. Perhaps the best current tool for Planet 9 searches is the Subaru Telescope's Hyper-Suprime Cam, a wide-field camera that combines a relatively large field of view with the light-gathering power of an 8.2-meter telescope. Teams have used this instrument to conduct systematic searches in the regions most favoured by Planet 9 models, imaging the same fields over multiple nights to detect motion. As of this writing, these searches continue, gradually covering more area, slowly ruling out regions where Planet 9 is not. Another complication is the Milky Way. If Planet 9's current position places it against the backdrop of the galactic plane, where stars are dense and the sky is crowded, detection becomes even harder. the millions of faint stars create confusion, making it difficult to identify moving objects reliably. Many searches therefore avoid the galactic plane initially, focusing on regions of clearer sky, even though this means potentially missing the planet if it happens to be in a difficult region. Sky brightness from moonlight, atmospheric conditions, and light pollution all affect the ability to detect faint objects. Searches must be conducted during dark time when the moon is down, ideally from remote sites with dark skies and good atmospheric stability. Weather inevitably causes lost observing nights. Telescope maintenance and competition for observing time from other projects limit availability. All these factors mean that even dedicated search programs can only cover limited sky area per year. The technical challenge of finding Planet 9 is thus multifaceted. Extreme faintness requiring the largest telescopes and longest exposures, slow motion requiring multiple observations and careful analysis, large search area requiring years of systematic surveying, and competition for telescope time requiring careful prioritization. These challenges explain why, despite years of searching and strong theoretical motivation, Planet 9 remains hidden, if indeed it exists. While the direct search for Planet 9 continues, another approach has proven equally valuable: systematically finding and characterizing all distant objects in the outer solar system. Each new discovery adds to the census of trans-Neptunian objects, providing additional data points to test the Planet 9 hypothesis and refine the predictions about where the planet might be. This patient accumulation of evidence proceeds steadily, with major discoveries announced every few years. In 2018, a team including Scott Shepherd announced the discovery of 2015 TG387, an object quickly nicknamed the Goblin, due to its discovery being announced near Halloween. The Goblin's orbit is remarkable. Its perihelion is about 65 astronomical units, well beyond Neptune, and its semi-major axis is approximately 1,170 astronomical units, giving it an orbital period of about 40,000 years. The orbit aligns with predictions from Planet 9 models, with its argument of perihelion clustering with the other extreme detached objects. The Goblin is significant because it was discovered independently of the original Planet 9 predictions, yet its orbital properties match those predictions closely. It serves as a prediction, confirmation rather than the data used to create the hypothesis, strengthening the case that the observed clustering is real rather than an artifact of small number statistics or biased observations. In the same year, astronomers announced 2018 VG18, nicknamed Pharut for being, at the time of discovery, the most distant object known in the solar system. Pharut orbits at about 120 astronomical units currently, though its full orbit is not yet well determined. As observations accumulated over subsequent months and years, its orbital elements gradually came into focus, providing another data point for outer solar system dynamics. In 2021, Pharut was surpassed by the discovery of 2018 AG37, nicknamed Far-Pharut, with a current distance of about 132 astronomical units and a perihelion of 27 astronomical units, close enough to interact with Neptune. Far-Pharut's extreme orbit, with semi-major axis around 380 astronomical units and orbital period about 1,000 years, represents another example of how Neptune, and potentially Planet 9, shape the outer solar system. The fact that its perihelion is near Neptune's orbit suggests it might be scattering off Neptune, yet its aphelion reaches into the realm where Planet 9's influence should dominate. Each of these discoveries requires patient observation. The initial detection comes from systematic surveys, usually wide-field telescopes, repeatedly imaging strips of sky and looking for objects that move between exposures. Once a candidate is identified, follow-up observations over months and years are necessary to determine its orbit accurately. For distant objects moving slowly, establishing a precise orbit can take a decade or more of observations. The orbital calculations are complex. Astronomers must account for the gravitational influence of all the known planets, particularly the giant planets whose masses dominate the solar system's dynamics. They must consider observational uncertainties, the fact that each position measurement has some error. They use sophisticated orbit-fitting algorithms that find the orbital elements most consistent with all available observations, while also estimating the uncertainty in those elements. As more observations accumulate, the orbital elements become better constrained. Initially, an object might have an orbit determination that's consistent with a wide range of possible ellipses. Years later, with dozens of observations spanning a significant fraction of the object's orbit, the uncertainties shrink dramatically. This gradual refinement allows astronomers to determine not just where the object is now, but where it will be far into the future and where it was in the past. Beyond professional surveys, citizen science has contributed to the search. Projects like Backyard World's Planet 9 recruit volunteers to examine images from surveys looking for moving objects that automated algorithms might have missed. The human eye remains remarkably good at pattern recognition, and distributing the workload across thousands of volunteers makes it possible to examine datasets thoroughly. Citizen scientists have discovered dozens of brown dwarfs, objects intermediate between planets and stars, and continue to find new trans-Neptunian objects. The broader search extends beyond optical wavelengths. Infrared surveys, particularly data from the Wide Field Infrared Survey Explorer, known as WISE, have been used to search for Planet 9. Massive objects, even cold ones, emit thermal radiation in the infrared. Planet 9, if it exists, should be warm enough from internal heat to emit a tiny amount of infrared radiation. WISE surveyed the entire sky in infrared wavelengths, and careful analysis of its data could potentially reveal Planet 9 if it's in the surveyed regions and bright enough in infrared. However, WISE searches have not yet detected Planet 9, which helps constrain its properties. If the planet existed at certain distances and brightnesses, WISE should have seen it. The non-detection therefore rules out some combinations of orbital parameters and physical properties, narrowing the range of possibilities and guiding future searches. Each new discovery, each new observation, each refined orbit adds to our understanding of the outer solar system's architecture. We're gradually building a three-dimensional map of the trans-Neptunian region, identifying where objects cluster and where gaps exist. We're seeing which orbits are stable over billions of years and which are transient, surviving only temporarily before ejection or collision. We're witnessing the slow gravitational dance of small bodies influenced by Neptune, by each other, and potentially by Planet 9. This approach exemplifies how astronomy often progresses, not through single decisive observations that immediately answer questions, but through patient accumulation of data, gradual refinement of models, and slow emergence of patterns from noise. The search for Planet 9 has become inseparable from the broader project of mapping the outer solar system, understanding its dynamics, and reconstructing its history. Whether or not Planet 9 exists, this work illuminates our cosmic neighborhood's structure and evolution. The discovery of Planet 9, if it occurs, would represent far more than just adding a ninth planet to the solar system's roster. It would fundamentally reshape our understanding of planetary system formation, evolution, and architecture, with implications extending far beyond our own solar system to exoplanetary systems throughout the galaxy. First and most importantly, Planet 9 would complete the census of major planets in our solar system. For centuries, we've wondered whether our catalogue of planets is complete, whether hidden worlds might orbit in the outer darkness. Each major planet discovery, from Uranus through Neptune, suggested the possibility of more. Finding Planet 9 would vindicate this suspicion and provide closure to the question of solar system completeness, at least for planet-sized objects. But more significantly, a super-Earth in our outer solar system would fill a conspicuous gap in planetary types. The solar system currently contains terrestrial planets up to 1 Earth mass, then a gap, then ice giants starting at 14.5 Earth masses. Yet, exoplanet surveys reveal that super-Earths, planets between 1 and 10 Earth masses, are extraordinarily common around other stars. They may be the most common type of planet in the galaxy. The absence of a super-Earth in our solar system has been puzzling, even embarrassing. Finding one, even at great distance, would align our solar system with the broader population of planetary systems. The existence of Planet 9 would strongly support planetary migration theories. The NICE model and other dynamical models of early solar system evolution proposed that the giant planets didn't form in their current locations but migrated significantly, with Jupiter moving somewhat inward and Saturn, Uranus, and Neptune moving outward. These migrations were driven by gravitational interactions with the disk of small bodies that populated the early outer solar system. If Planet 9 exists on its eccentric distant orbit, it likely didn't form there. Its orbit requires some dynamical mechanism to place it in such a configuration. The most plausible mechanisms involve migration and scattering, matching the processes proposed for the other giant planets. Planet 9 would thus serve as direct evidence that the solar system experienced dramatic dynamical evolution rather than forming in a quiescent, stable configuration. Understanding Planet 9's composition would inform theories of planet formation. If it's icy like Neptune, that suggests it formed beyond the snowline, where water and other volatiles could condense, and either formed in place or migrated outward from the original ice giant formation region. If it's rocky, that suggests it formed in the inner solar system and was ejected outward, requiring violent scattering events. If it has a substantial hydrogen-helium atmosphere, that indicates it finished forming before the gaseous component of the protoplanetary disk dissipated. Each compositional possibility teaches us about timescales, available materials, and dynamical processes during planet formation. Currently, our understanding of super-Earth composition comes entirely from exoplanets, whose compositions must be inferred indirectly from their mass, radius, and atmospheric spectra. Having a super-Earth in our own solar system that we could potentially study in detail would provide ground truth for interpreting exoplanet observations. Planet 9's existence would also illuminate the efficiency of planet formation in the outer solar system. Why did only 4 giant planets form rather than 5 or more? Was Planet 9 ejected because the formation region became crowded? Did Jupiter and Saturn's rapid growth monopolize the available gas, leaving insufficient material for additional giant planets? Or did Planet 9 simply form in a region with less material, growing large enough to dominate locally, but not large enough to compete with the inner giant planets? The broader implications for exoplanetary systems are profound. Many observed exoplanetary systems are compact, with multiple planets orbiting closer to their star than Mercury orbits the Sun. Others show evidence of dynamical instability and planet-planet scattering. Some systems may have ejected planets during their formation and early evolution. Planet 9 would provide a local example of planetary migration and potential ejection, offering detailed insight into processes that we can only infer for distant systems. From an astrobiological perspective, Planet 9 raises intriguing questions. Could such a distant, cold world harbour life? Almost certainly not on its surface, where temperatures hover near absolute zero and sunlight provides negligible energy. But if Planet 9 has large moons with subsurface oceans maintained by tidal heating, those environments might be habitable. Europa, Enceladus, and potentially Titan demonstrate that habitability in the outer solar system doesn't require close proximity to the Sun. Planet Nine's moons could be added to the growing list of potentially habitable environments in our solar system. The discovery would also affect the search for additional planets or massive objects in the outer solar system. If one planet hid successfully beyond Neptune for all of human history, might others exist even farther out? Planet Nine's discovery would motivate searches for Planet 10, 11, and beyond, pushing the boundaries of the solar system census to ever greater distances. For the history and philosophy of science, Planet 9 represents a case study in how major discoveries unfold in the modern era. Unlike Neptune's discovery through mathematical prediction, followed quickly by telescopic confirmation, or Pluto's discovery through systematic photographic surveys, Planet 9's story is one of gradual accumulation of indirect evidence, statistical analysis of populations, and patient observational campaigns. It demonstrates how contemporary astronomy increasingly relies on large data sets, computational modeling, and collaborative international efforts. Whether or not Planet 9 exists, the search for it has already advanced planetary science by motivating surveys that discovered many other trans-Neptunian objects, by spurring development of more sophisticated, dynamical models of the outer solar system, and by highlighting the importance of the solar system's outskirts for understanding its formation and evolution. The journey toward answering the question has proven as scientifically valuable as the answer itself will be. As you lie here in the darkness, perhaps feeling sleep approaching, consider the nature of the search for Planet 9, what it teaches us about discovery, about patience, about the long arc of human knowledge, seeking to understand our place in the cosmos. This is not a search driven by urgency or marked by dramatic breakthroughs, but rather one characterized by methodical observation, careful analysis, and acceptance that some questions take decades to answer. Astronomical discovery has always required patience. William Herschel discovered Uranus in 1781, but proving it was a planet rather than a comet took months of observation, tracking its motion. Neptune's discovery in 1846 came after years of analysing Uranus's orbital perturbations. Pluto's discovery in 1930 resulted from a systematic search that examined thousands of photographic plates over years. Modern astronomy continues this tradition, but on even larger scales, with searches spanning decades and involving international collaborations, examining data from multiple instruments. The search for Planet 9 exemplifies this patient approach. Batygin and Brown published their analysis in January 2016, nearly 9 years before this writing. In those 9 years, surveys have imaged thousands of square degrees of sky, discovering dozens of new trans-Neptunian objects, refining orbital models, gradually constraining where Planet 9 might be and ruling out where it isn't. No dramatic announcement has been made because astronomical discovery rarely works that way. Instead, probability gradually shifts from uncertain to likely to nearly certain as evidence accumulates. This patience frustrates our modern desire for immediate answers. We live in an era of rapid information flow, where questions posed to search engines return answers in milliseconds, where news cycles measure time in hours rather than days. The idea that a question as seemingly simple as, "Does a planet exist in our solar system?" might take a decade or more to answer seems almost absurd. Yet the universe operates on its own timescales, indifferent to human impatience. Planet 9, if it exists at 500 astronomical units, is so distant that light takes about 69 hours to travel from the Sun to the planet and back. This means the light we would detect from Planet 9 began its journey days ago. And if the planet changes somehow, we wouldn't see that change for days. On human timescales, this delay is barely noticeable, but it reminds us that observation of distant objects is always observation of the past, and that information propagates at finite speed across cosmic distances. The planet's orbital period, potentially 15,000 years or more, means humanity, in our current form, has existed for only a few of the planet's orbits. All of recorded human history, all of civilization, spans less than one planet 9-year. The planet has been in approximately the same region of sky throughout all of human existence. If ancient astronomers had possessed our telescopes and searched systematically, they might have found it, and to them it would have appeared stationary against the stars, moving so slowly that multiple generations of observers would be needed to detect its motion. This vast orbital period also means that Planet 9's current position in its orbit is essentially random from our perspective. We happen to be searching for it now, at this particular moment in its 15,000-year journey around the Sun. It might be at perihelion, relatively bright and close, making detection easier. It might be at aphelion, at maximum distance and faintness, rendering it nearly impossible to detect with current technology. We don't know, and this uncertainty affects the search strategy and timeline. The statistical nature of the evidence for Planet 9 also requires patience to evaluate properly. The orbital clustering of distant objects is suggestive, but statistics deals in probabilities, not certainties. As more objects are discovered, the statistical significance either strengthens or weakens. Currently, with each new discovery that fits the predicted pattern, confidence grows, but a single discovery of a distant object with orbital properties strongly inconsistent with Planet 9 models would challenge the hypothesis significantly. This is how science works at its best, not through dogmatic insistence that a hypothesis must be correct, but through openness to evidence both supporting and contradicting. The astronomers searching for Planet 9 are simultaneously trying to find it and trying to rule it out. They examine alternatives carefully. They question their assumptions. They recognize that even compelling indirect evidence doesn't guarantee existence. Consider what we learn from the search, regardless of its outcome. If Planet 9 is found, we gain a new world to study, new insights into solar system formation, confirmation of our dynamical models. But if extensive searches rule out Planet 9's existence, we gain different knowledge. That the orbital clustering has some other explanation, that our models of the outer solar system require revision, that perhaps we don't understand the observational biases as well as we thought. Either outcome advances understanding. This patience extends to the technology required for the search. Current telescopes can detect Planet 9 if it's in the right location and reasonably bright, but they require years to survey the necessary sky area. Future telescopes, particularly the Vera C. Rubin Observatory, with its wide-field legacy survey of space and time, will survey the entire visible sky repeatedly, reaching the depths necessary to detect Planet 9 nearly anywhere in its orbit. This survey will begin operations in the mid-2020s, and over its planned decade of operation, will either find Planet 9 or place such strong constraints on its properties that alternative explanations become necessary. We see here a principle that applies throughout astronomy. Sometimes the answer to a question must wait for technological advancement. Astronomers in 1900 could not have detected Planet 9 even if they had known exactly where to look. Their telescopes and photographic plates weren't sensitive enough. Their understanding of orbital dynamics wasn't sophisticated enough. Their computational tools weren't powerful enough. The question had to wait for the technology to mature, for knowledge to accumulate, for the right combination of theoretical insight and observational capability to emerge. There's a kind of wisdom in this patience, a recognition that the universe is vast and complex, that our understanding grows gradually, that some truths reveal themselves only to those willing to wait and search and question over years or decades. It's antithetical to modern rhythms, but perhaps more aligned with deeper patterns of human learning and discovery. As your thoughts drift and consciousness begins to slide towards sleep, you might contemplate this. Somewhere in the darkness beyond Neptune, either a planet orbits silently, completing another increment of its millennial journey, indifferent to whether we find it or the clustering we observe has some other explanation we haven't yet fully grasped. Either way, the search continues. Telescopes scan the sky, data accumulates, astronomers analyze, model and publish. Slowly, incrementally, the question approaches resolution. The universe is patient. It has existed for nearly 14 billion years. Our sun has shone for 4.6 billion years. Planet 9, if it exists, has orbited for all of that time. Unseen, unknown, simply being. A few more years or even decades of searching is nothing against these timescales. We search with the patience that the cosmos itself teaches us, knowing that understanding comes not to those who demand immediate answers, but to those who ask good questions and pursue them wherever they lead, for as long as they must. And so we conclude this journey to the edge of our solar system, to the hypothetical realm of Planet 9, that ghost in the outer dark, whose presence we suspect, but have not confirmed, whose orbit shapes distant worlds while remaining itself invisible. Tonight we've explored the evidence written in the strange alignment of icy bodies, the mathematics that points to an unseen shepherd, the patient search that continues across years and will likely continue for years more. Planet 9 remains uncertain, a hypothesis supported by compelling evidence, but awaiting the decisive observation that would transform it from possibility to confirmed reality. The telescopes continue their vigil. The surveys gradually cover more sky. Each clear night brings another opportunity for detection, another field imaged, another set of moving objects identified and tracked. Somewhere in the accumulated data, perhaps the faint point of light that is Planet 9 already exists, waiting for the right analysis to reveal it. Or perhaps it remains just beyond current detection limits, requiring one more generation of instruments to finally bring it into view. Whether Planet 9 exists or not, the search itself matters. It has taught us about the outer solar system's architecture, revealed new distant objects, refined our models of planetary dynamics, and demonstrated that even in our own cosmic neighborhood, profound mysteries remain. We've learned humility, recognizing that something as large as a planet could hide from us for all of human history, simply because space is vast and light grows faint with distance. Imagine, as you drift towards sleep, that world in the darkness, if it exists. A frozen sphere of ice and rock, perhaps 50,000 kilometers in circumference, massive enough to hold moons and reshape orbits yet invisible to our finest telescopes. Its year spans empires. Its day passes in hours. The sun from its vantage appears merely as the brightest star, a brilliant point that provides little warmth and less comfort. It orbits in silence, in cold, in darkness, patient as the cosmos itself, waiting to be found. Or imagine the alternative, that the clustering we observe arises from causes we haven't yet fully understood, that the outer solar system's complexity exceeds our current models, that nature has surprised us again with its variety and subtlety. This too would be a kind of discovery, a recognition that the story of our solar system continues to unfold in unexpected ways. The search continues tonight. Even as you rest, telescopes on distant mountains track the stars, recording photons that have traveled across the solar system and beyond, building the datasets that will gradually reveal what lies in the outer dark. Astronomers examine the data, run the simulations, refine the models, publish the papers, and return to the telescopes again. This is the patient work of discovery, the slow accumulation of knowledge, the gradual lifting of ignorance's veil. Sleep peacefully tonight, knowing that the cosmos holds its mysteries gently, revealing them in time to those who seek with patience and care. Dream of distant worlds, of frozen plains lit by starlight, of long orbits and patient searching. Dream of the moment, perhaps years from now, when a faint point of light in a CCD image shifts slightly between exposures, and someone realizes that after years of searching, Planet 9 has been found. Or dream of the alternative understanding that will emerge if extensive searches rule it out, the new insight into orbital dynamics that will replace the planet hypothesis. Thank you for joining us here on Whispering Universes as we explored this quiet mystery at the edge of our solar system. Let the patient rhythms of astronomical discovery carry you gently towards sleep, comfortable in the knowledge that whether we find Planet 9 tomorrow, or decades from now, or realize it was never there, the search itself illuminates our place in the vast cosmic dark. Sleep peacefully, dream deeply, and know that the search continues.